So here we're going to find the displacement of a cantilever beam that has a point load F applied at its free end. And the way that we're going to do that is by using the method of integration to find our deflection. So we have this beam, it has a length L, it's fixed on one end. On the free end we have a transverse load F acting downward. Let's define our x coordinate. So we're going to say that x is positive to the right, with x being equal to 0 at the fixed end, x equals L at the free end. So the first thing we need to do when we're solving a problem like this by integration is we need to come up with an expression for the moments, and the way that we'll do that is by creating a shear and moment diagram. So let's start with the free body diagram, so that way we can come up with our shear and moment diagram. So we know on this beam we have our applied load F, and then the reactions at the wall. We have a reaction in the y direction because this is a cantilever beam, because it's a fixed boundary. It's fixed in the y direction, it's fixed in the x direction, and we know that we'll also have a reaction moment. So we've got a reaction moment that we'll draw in this direction. Okay, so if we sum forces in x, there's really nothing to see because there are no forces in x, so we just see by inspection all the forces in x are 0 because there are 0 forces. If we sum forces in y, we'll have the reaction force in y, Ry, minus F equal to 0, which tells us that Ry is equal to F. And we'll sum our moments, and we'll do that at about this point. Let's call this point A here against the wall. So we sum our moments about point A, and we have m minus F times L equal to 0. So we have that m is equal to F times L. And so this is enough information here to where we can go ahead and make a shear and moment diagram. And the goal of these diagrams, again, is to come up with an expression for the moment as a function of position on the beam. And so we'll do our shear diagram first. Since our reaction force is F, we know that we're going to start at F. Then there's nothing happening all the way across the beam until we get to that concentrated load, which brings it back down by F to 0. So this is x equals L right here. Our moment diagram, our reaction moment was positive FL, so that means when we make the moment diagram, we come down to negative FL. So this is just like what we've done in statics and in different parts of this course. We know that we'll have a slope of F looking at our shear diagram, and so over the length of the beam we will come up by F times L to get back to 0 at L. Okay, so the expression for our moment, we have this y-intercept, negative FL. We're just making an equation of a line now using our moment. So we have a straight line, we have a y-intercept of negative FL, if you consider the moment axis to be like a y-axis. But our intercept, though, is negative FL, and then we have a positive slope F. So we'll have our equation of a line is negative FL plus X. Okay, so now that we have an expression for the moment, we can go ahead and use this method of finding deflections by integration. So there's an overview of kind of a derivation of this method and how it works, and a few details in the lecture notes. We're going to go ahead and do an example, finish off this example though. So just so you can get an idea of how the process works. So for method of moments, we know that this relationship holds EI times d squared v dx squared is equal to the moment, which is a function of x. And remember that v in this equation refers to the displacement of the beam, and that's the vertical displacement of the beam, so that would be the displacement in the transverse direction to the beam. So in this case it would be up and down, since that's transverse to the beam. And then we can go ahead and take integration. So we'll integrate this equation once, and that will give us EI dv dx. Before we integrate, sorry, I failed to write out our expression for the moment here on this first line. So we have EI d squared v dx squared equals the moment m of x, which is equal to minus FL plus Fx. So we come back down, we started taking the integral of this first equation. We have EI dv dx is equal to, and then we take the integral of the right hand side. That's negative FLx plus Fx squared divided by 2 plus a constant of integration, which I'm going to call C1. Alright, we'll take another integral, and we'll have EI multiplied by V is equal to negative FL x squared divided by 2 plus Fx cubed divided by 6 plus this first constant of integration times x plus another constant of integration, which I'm going to call C2. Alright, so I'm going to label these equations number 1 and number 2, because we're going to use them. So this first equation, EI dv dx is the slope of the beam. You'll sometimes see dv dx written as theta, and then v, like we mentioned in equation number 2, is the deflection of the beam. So you can see that we can actually write an equation then for the deflection of the beam as a function of position on the beam if we can come up with these constants of integration. So to find the constants of integration, we're going to use boundary conditions. So let's recall that for this cantilever beam, if we come back up and look at it for a second, we can see that our boundary conditions, we have a few known boundary conditions, meaning at one end of the beam, or some point along the beam, well, boundary conditions at this end, at certain points in the beam, we might know something about the displacements or the slope in the beam. So in this case, for a fixed end, we know that at the fixed end, so at x equals 0, we know that v is equal to 0. We also know that x equals 0. The slope is also equal to 0. So dv dx equals 0. Okay, so these are just the general boundary conditions for a fixed boundary condition, a fixed end. So if we come back down, we can use those boundary conditions in equations 1 and 2 to solve for the constants of integration, and then we'll have a full expression for deflection in the beam. Okay, so from the boundary conditions, and I'll repeat those down here, but from our boundary conditions, which I will abbreviate as BCs, so we know that V at x equals 0 So the deflection at x equals 0 is equal to 0 because it's a fixed boundary condition. And then we also know that the slope dv dx at x equals 0 is equal to 0. Okay, so we're going to use these boundary conditions in the equation. So let's start with equation 1. Let's sub that. We'll sub in the second boundary condition into equation 1, that dv dx equals 0 when x equals 0, and we'll have that ei. We know dv dx is 0 at x equals 0, so ei times 0 is equal to, and then these terms in our equation, if there's an x is equal to 0, so our first term is 0, plus f times 0 squared over 2 is 0, plus c1. So we end up with c1 equals 0. So our first constant of integration is just 0. Alright, now we're going to plug in the boundary condition that says that v equals 0, x equals 0. We're going to use that in equation 2. And we're also going to use that c1 is equal to 0 in equation 2. So this is just like you do in calculus. So we have ei. We're saying we know our boundary condition says that v is equal to 0 when x is 0, so it's ei times 0. And that's equal to this first term, fl x squared over 2, x equals 0 though, so that's 0, plus fx cubed over 6, x equals 0, so that is also 0. c1 times x is 0, so that's also 0. All of that plus c2. So again, we have another constant of integration that's equal to 0. So c2 is equal to 0. So we can rearrange, we can sub in c1 and c2 to this equation 2 and rearrange to write an expression for the deflection v at any point along the beam. So, and that will give us that, well, before we rearrange, we'll just write the equation how we had it. We have the ei times v equals minus fl x squared over 2 plus fx cubed over 6 and so yeah, this, let me clean up this 6 a little bit. So this is telling us right here, give us an expression for v in terms of x. This problem asks us though what v is at the free end of the beam where x is equal to L. So to find v when x equals L, all we have to do now is plug in L into this equation here, which is the expression for v. So we'll have e I times v is equal to negative fl. For x, we're plugging in L, so we'll have L squared over 2, and then plus f times, for x we're plugging in L, so we have fl cubed divided by 6. Okay, so if we were to simplify this, which we'll do, we'll have ei times v is equal to, if we did the algebra, we'd have simplified these fractions, we'll have minus fl cubed over 3. And then if we just do the last bit of algebra to rearrange this to put it to solve just for v, we have v is equal to minus FL cubed divided by 3EI. Okay, so that's telling us that the displacement is in the downward direction. So for a force F at the free end, we're going to have a displacement in the of the tip. The tip will displace in the downward direction by FL cubed over 3EI.